Hello everyone, this is Mr. Joseph from Lendshield AI Research Group. So in this session, I'll be taking you through model training, evaluation, leakage audit, and the model architecture of the models we used. So basically, we focus on module 1, application gatekeeper. So we are building two modules, load monitor also. But due to time, we have said first focus on module 1 application gatekeeper until it's MVP. Um, uh, Here, presentation agenda. So I have the problem set up throughout number 11, where I speak about MVP readiness. This is just aligning what I will be going through from number 1 up to number 11. The problem. So here we are looking at the pre-disbursement default screening. So looking at what are we actually predicting. So so we are predicting some fee target Y. So our target is defaulted, which we engineered. So we just engineered those targets. So we have pre-disbursement features. So like the loan amount, duration, age, business type, and the rest. So now, so we have the model only uses information that is available before disbursement of the loan. That is so those features which are not seen before the disbursement of loans, such as balance, the repayments, those ones are forbidden because they are the model will be shooting into the future. So here, present a pipeline from application where application features taking through the model producing for us the probability, and then going through the threshold which I will describe in the next slides what threshold is. So as we are building, these are now the steps we are taking as we are going to train our models. So we look at pre-audit leakage prevention. So these are just the initiatives we took as engineering discipline, not like in response to the auditing that we did after, but these are just the initial steps we took to prevent leakage. So we look at post-outcome proxy features. So post-outcome proxy features, what are we meaning? So these are only features that are going to be seen after disbursement, I mentioned before. So our code just scans the column name and identifies those features like repayment, missed areas, penalty, and then drops them. So why? Because the model want to be able to see those features. So then we have global target encodings. So so things like district encoded, those ones there, and then how we just dropped them by column name also. Like if the names like group district encoded, business type. So why? Because because that is like label leakage. So if we compute those encoded features on full data set before device splitting them, so it will result into label leakage. So I'll progress to, so how did we ensure institutional robustness as we progress? So we looked at so issues like so how? So we have concerns of if we just split randomly. So if we just split randomly like that, the modules will just identify given circles loan patterns. So, and therefore the modules will not be robust to go on the new circles or microfinance. Therefore, the model will just predict based on certain pattern, and yet that is not going to be true in the real world where we want to deploy these modules to predict from different circles where the data didn't come from the data we used to train the model not coming from those circles. So for that case, we looked at so group shuffle split. So what do we mean by group shuffle split? So this is where now we find the split So the train will take in circles, let's say circle A, B, C, D. And then the validation will take in, let's say, circle I, J. And then the test will also take place on different what circles. So no data from a given circle I is going to be used in training. So model trains completed on different circles and then is validated on different circles and tested on different what circles. So now, now we tried different random state because different random states or seeds produce for us different categories of split. But our data set already has an imbalance. So what is that imbalance there? So I think that our data set has a balance. We already saw previously that we have 16% defaults and the rest of the Gundi are non-defaults. So already there is an imbalance. So when we split, so we are going to find cases of like, so Circle AJ word, so they have defaults which are in maybe 15%, and then the model is training on data maybe Circle A to J, and it has a default rate of 30, and then it's being tested on circles maybe XY, which has default rate of maybe 5%. So now, in that case, we have to try different Gundi to produce for us different what? Splits. So, and then maybe we want to get something like which a little bit, they are a little bit equivalent. So in that case, we tried many attempts, but then we came out with 8 that produces for us at least balanced set that whereby the default rate for 2023, 20, and 30 just somehow. So we decided to use that. So now we are looking at model training on of course, now we can see the production here. Model is going to be training on a very simple data set. Why are we saying simple? There are very few defaulters, and then compared to the number of what? Of non-defaulters. Therefore, if a model, the accuracy can be high, even for a dumb model, which is just going to say everybody is not a defaulter, this model is just going to be able to get like 76% accuracy, yet it is predicting nothing at all. So we handle that in a later case, whereby now we use stability run. We don't just use one threshold. So I will progress. So processing pipeline. So and the F2 threshold tuning strategy. So we take through the pre-processing stage, and then we also talk about the F2. So we look at the numerical features. What did we do? So we did the simple imputing, so the median, or the numerical features, robust scalar, where we use the interquartile range, not the standard deviation. So interquartile range, whereby now you find you put a boundary, you take the outliers. So and then you use the concept of interquartile range which is robust to outliers in order to compute to scale. So it will help us to handle extreme values without distortion. So we know why are we scaling? We are scaling because our modules basically they learn better with small values. They struggle with those large values. So categorical features. So we use simple imputers still. So we fill with the most frequent one hot encoding. So now we get like numerical labels for those categorical features through one and like creating a given column. For example, let's say Job is doctor. So we just create a column and be like, is doctor? So 1 or 0, 1 or 0, like that. So so training. So we did only training on the like we fitted the data on only training data set. So to prevent leakage still. So validation and test. So they used the train fitted parameters. So 0 proportion leakage. So we have F2 threshold tuning. So our focus was on F2. F2 is let's say a metric that creates balance between precision and recall. So when I talk about precision, I mean like, let's say when our model predicts that, okay, true positive, like our model predicts this is a defaulter. So what's that probability that actually the person is a defaulter? So so that is what we call precision, so the true positive. So then so then we look at a recall. Recall is like if we have for like 100 defaulters, how many of those defaulters do we actually cache? So out of the 100, so if we are able to find cache all the 90 in our set, so we say our model has a recall of 0.9. So but then F2, these two of them, they have like conflicts. They conflict among each other a lot. They conflict among each other, precision and recall. So if you threshold simply is like a boundary, a mark whereby you set that mark boundary to determine either default or non-default. So you can set a search threshold of, let's say, 0.5. So that means the model produces for us like probability. But then we need a complete decision whether whether it is defaulter or none. So now it is through the threshold which we set during validation, we are able to determine that this is a defaulter or none. So if we put a threshold of 0.5, that means that only borrowers whose probability of default is equal or greater than 0.5 are quoted as defaulters, but those ones below are none. Now, if you put too low, so that means like when we put too low, our recall is going to be like very high. And then if we put too high, so sorry, if we put too low, we have our precision high. Like noise is going to be less. When we say this is a defaulter, there is very big probability that it's actually a defaulter. But then the recall reduces. We are going to miss very many true defaulters. So because of that conflict, now we bring in F2. So F2 balances, but then gives more weight to recall. Because why we say recall? Because of the policy we are using in finance, that missing defaulter costs the full loan principal. Then sorry, like in lending, so missed defaulter costs the full loan principal. A wrong rejected applicant costs only the interest margin. So that's why we look at recall. So we are like in the circle, we want to act in the circle, the defaulters, we don't want to miss them, we want to actually catch them. So we want to maximize. So it's better for us to falsely, like when we say it's defaulter and it's not defaulter, it's okay. We are missing some few interests than us missing the actual defaulters. So quickly to the next. So so we did some leakage audit. So as we promised that our Gundi performance was too good to be accepted, so we had to do some auditing and we established some hypotheses here. So I will just continue. So those are the hypotheses we based on, and every action that we carried in leakage audit was in need of resolving a given hypothesis. Just to go through, like, so we look at sharp global importance. So we look at importance, the contribution of each feature in that. So then we get a graph. So in that graph, so we look at the contribution of a feature. So which one is too dominating? So if it is too dominating, how was that feature built? Is it a built feature? Is it a feature that's coming post disbursement or not? So, and then we happen to catch a feature like interest burden, which we see that this feature was built according to so this feature was built, let's say it was defined as areas over balance. So interest areas, the interest we are demanding you over your balance that you have, that ratio there. So that is a post disbursement. We can only know balance after you have gotten the loan. So we removed that, and then of course the performance had to come to more realistic values. So so those are the auditings we did, and yeah. So I'll progress to the next slide. So now here we look at the other challenge that we had in the other side, whereby now splitting, why we are not trusting one split only. It's not good. So I explained that earlier. So now what do? We are going to do So what are we doing? We are going to do stability runs. So here we are just, I called it like a validation lottery problem. So we are saying, what if a circle E and F happen to have clean data that perfectly favors XGBoost? So that's the problem of single split. And all this came about when there was a lot of deviation between the validation result and the test results. So it happened like, if you look at the loans that fail in validation were like very simple circles, which were very easily predictable. They had very few defaulters, all are non-defaulters, therefore actually it's a high recall high. So things were just there. So we had to do stability tests. What is stability tests? We had to stability test is we ran very many splits. So whereby we used about 6 splits, let's say that was it. So we started with a seed of 100 seed, which is like the random state of 100, and then we went to 101 like that. So producing different splits, different circles falling differently. So so if we can look at the seed 1001 like that, different circle falling in different categories, and then there we get the circles, and then afterwards we train, and then when we train, then we validate. After validating, then we test. After testing, then we get those metrics. After getting those metrics, then we do another split. Then we get different circles again, ABCD in train, and then circle B, ABH, and DEF in splits. And then we do validation, and then we again test. We get the metrics. Now, after getting the metrics, we now start getting the mean and standard deviation, and then the range. So we get the mean of F2. So so when we have the mean of F2, and then we have standard deviation. So the one that has a very low standard deviation, that means that model is stable across different circles. Okay, not stable, but more stable than others. Yeah. And then definitely its mean is also bigger than other F2 means. Our focus is on F2 means. So our threshold tuning was focusing on the threshold that gives us the biggest F2 score, because I explained that earlier why we're focusing on F2 score. So going to the next. So now here we discuss the architecture of the modules that we used, okay, that I used in food. So my colleagues trained other modules. So to show that we understand the architecture, how these modules we have trained learn. How do they learn? How do they get to predict all these things? So looking at random forest. So random forest basically, as you're hearing, it's forest. So creating trees, where those trees, a given tree will create different branches. Now, so we are looking at it, for example, an organization just having one loan officer. Now, that loan officer is going to come up with set of rules. So when it comes up with sets of rules, which has simple answer, true or false. So for example, just says, is age greater than 25. So if the age is greater than 25, go decide. Less than 25, go decide. So in a given subpile, they are going to be like defaulters, maybe 80. Like 80% of defaulters, and then another pile has different percentage of defaulters, and then it picks a given subpiles. Then it defines another rule, let's say amount greater than 2 million, and then it has two answers. Gets a different subpiles, get different subpiles. A given pile will have percentage of defaulters. It keeps on building like that. But then if we use just one loan officer or one tree, it will have a problem of memorizing a given rule or performing just a stupid rule by saying that if someone is greater than age is greater than 25, is going to be a defaulter, because people in category of greater than 25 had default rate of what? 80%. So for that case, it is going to be a wrong decision. Therefore, what do? We bring multiple loan officers. We make different trees. So all of them defining their rules according to that. Now, those rules, the last tree produces a given probability. So like, let's say 60%. So even another tree will create. Now, the mistake that was made by sending a given borrower in who is grade 20 as a defaulter yet was not, will be cleared by another mistake made by another tree. So mistakes, always errors cancel via averaging. So we average the votes of those trees, and therefore we come with more stable results. So here we talk about the parameters. I'll just skip due to time factor. So this is how run the evaluation and the audit results. So he talked about thresholds. So the threshold as a mark of bar, the one that we determine to say is a default or not default, and we define it on validation, not on test. If we define it on test, it's like we are using exam results to make our rules, which is really a very wrong thing. Let's make our exercise to make the rules. So because we may end up loosening our rules because of exam results. So there we come in with the concepts of what? Threshold. The threshold, the bar. So our threshold is not just a single threshold, but we run through the loops. So we get the threshold that maximizes F2 score. All our threshold was aiming at maximizing F2 score. So now for that case, here, in the 6 splits, so this is the average of the threshold over the 6 splits. And this is how the thresholds deviate. That's the deviation across the 6 splits, this value here. And then F2 score, this is the F2 score average across the 6 splits, and this is the deviation, how it varies across the 6 splits. So this is F2 score for validation, and this is F2 score for testing. As we say that for every single split, we do train, we validate, we test, and then we get the average of all of them, then we get the standard deviation, and that's how we are going to base in order to test. So F2 score, I talked about it. Area under precision recall is like average of precision. So and then we look at rock area under the curve, so it's like the probability, like if we randomly decide to pick, let's say we randomly decided to pick grant probability, so a random defaulter and a random non-defaulter, if we decide to give them probabilities to those random defaulter and non-random, random non-defaulter, what is the chance that we are going to give the highest probability to a defaulter and a low probability to non-defaulter? So this is the probability that we are going to give high probability to a defaulter and low probability to non-defaulter. So this is pretty quite good. So, and still it is an average across the 6 splits, and this is the deviation. So I will just progress. So I've explained that as a modules, that's how it goes throughout as a module. So going on to explain XGBoost. So its architecture and how everything is working. So XGBoost is built like the random forest, but a little bit different, whereby every node or tree clears the error of the other. That is what I kind of like how these modules work. So let's say initially it will just start on the data set. So and then just initially, so it will give let's say probability to all the rows or all the borrowers and be like, so what is the percentage in our Gondi? 16% are defaulters. So it will say 16%, everyone is 16% defaulting. Now it build and then calculates the error, then realizes, okay, on actual defaulters, these guys are supposed to be 100% defaulters. So I have an error of 84%. And then on non-defaulters, you will realize that, I have an error of negative 16% because they're supposed to be 0%. So now it has calculated the error. So it relies completely on the error pattern. Now, building its first tree, the first tree is going to aim at correcting the what? The error. So, so it has an error. So it's going to look at the code, the biggest error, because the logic attracts to the group that has the biggest error. So it's going to look at the biggest error and then say, what is it that is in common for all these borrowers that have, like we said, that has error of about 84%. So maybe it will find out that, okay, the common thing is that most of them had big savings. So it will now define a rule and be like, if saving is greater than maybe 5 million, then so that means it will get all those that have savings greater than 5 million. Then, of course, others will be having 80%. Others, of course, will be having that negative 16. Yeah, who are non-defaulters. And then I'll get the average of their errors. Maybe the average will be like, let's say 30%. So now it will say everyone in that set gets the what? The 80 what? I mean the 30% average. That is his rule. The rule is that I'm adding 30% probability on all those ones. So when it adds that to go on the average, so there's going to be this one who actually was negative. So he gets more. He had an error of negative 16. Remember, they said he has 16% of defaulting, yet he's not a defaulter. So gets more 30%, that becomes 46%. So when it comes to 46%, so the error has actually escalated the more. So, but the error for those ones which were 16, they have now increased. They're getting close to what they actually deserve for the defaulters who fall in categories of greater than 5 million savings. So now so we progress. The next tree will do the same thing. It will identify, oh, there is this guy who is now error negative 46. Why are we saying negative? Because they are supposed to have 0, and now they have 46. So they have an error of negative 46. So look at negative 46 and look at what is common among these people. Like they are claiming they have one. Maybe they will, so most of them from Kampala. So if borrower from Kampala, maybe is borrower from Kampala, so it will collect all borrowers or rows that are labeled with Kampala, averages them, their errors, and then what they get now is what they add to everyone who has a label of Kampala, and that's how it builds. So his rule is the average gets. So the average may be, because it was negative, of course some will be positive. So the average may be like, let's say negative, maybe negative 20. That means the 46 has to get, they deduct. So they deduct the 20. So they get back to 0. They have corrected the error that the other one created. So that's why it is XG boosting. So this one, it's rule. Now, if a new loan comes, it goes through, they keep just summing up. This one applies its rule, the other one applies its rule, this one applies its rule, depending if the person meets the what? The condition. If you are from Kampala and you get the summation from this. Greater than 5, you get the summation. And after, until the end of the tree, you get the final decision. So that's how this model works. So this is how this one was evaluated. I explained what these ones mean. And here is the comparison. So we compare random forest and XG boost. So we can see XG boost F score is good. So so we progressed. So for F2 score validation test, and then area under precision recall. So how tap transformer works. So I'll give an overview. So tap transformer. So traditional modules now have this problem of identifying patterns in those features, like features. So let's say like if we have let's say a feature, job. So job is doctor. So and then we have another column, income stability. So actually, doctor may have very good relationship maybe with like income stability. So very, very close. But in then traditional models, just hot encode is doctor, blah blah, fails to get those patterns. Now, tab transformer solves that. What does tab transformer do? So tab transformer is in okay, like I meant like I'm meaning job nurse and maybe job teacher. They may be kind of related with one particular, let's say, hidden personality. Is it trait? Yeah, hidden trait, maybe, which is like income stability. Yeah, maybe even region. Yeah, something like that. They are just related to a given, according to given trait. Now, these other modules fail to identify that. Now, tab transformer does that. How does it do it? So it hiddenly assigns vectors. So therefore, which has like a vector points. So now those vector points can be analogous to those traits which we are talking about, like income stability, maybe age, yeah, something like that. So now, so those vector points are what are used to come out with the probability. Now, the probability produces for us like the loss, whereby it relates with the actual outcome. And actual outcomes are like encoded into numeric values, so 0 and 1. So the vector points are fed into a function. Let's say it's a function of the logit function. So now, so that vector pointer is used to produce the probability. Now the probability, so let's say probability is very low. Now if the probability is very low, and yet the actual value of the outcome is 1, the one we are trying to predict. So when we subtract 1 minus the low probability, which is maybe 0.001, came from the vector points. Therefore, loss is high. So because you're going to, and it's greater than 0, loss is high. Our aim is to reduce the loss. So what does it mean? So it means we adjust the vector points. So, and then since the loss is high, the value is high. So let's increase the vector points in order to increase the what? The probability. And then so if we increase the probability, let's say probability increases. So we subtract 1 minus the probability, and therefore we reduce the loss. So that's how the vector points keeps adjusted. Now, how does the relationship between doctor and what comes in? So we don't just map that relationship by default. The relationship is going to be mapped, like the vector points are the ones that are going to tell us if these guys are really related in one way or the other. So because those values will be adjusted until they resemble. Why are those values adjusted? Those values we are going to be adjusted until they resemble if and only if they are able to reduce for us the loss. Are we going ahead to reduce the loss? We adjust NAS, adjusting it in relation to the doctor. Is it reducing the loss? So all of them are adjusted independently, but because they are aiming at one goal, they may end up resembling if actually the similarity is there. Remember, they are adjusted basing on the true outcome. So that is it. Now, how how that was the embedding layer, and then self-attention is like each of the features, they look at each other, so and then find out if there is a relationship between them. How do they find out that relationship? They get their vector points. So just speaking it, they get their vector points, they get the dot product. So we get a forward, when we get a forward vector, so that means that now these features are actually related to what each other. Let's say, so let's say a farmer. So and then farmer borrowing money. The job is farmer. The reason for borrowing money is in buy seeds. So buy seeds has its vector points, and buy seeds has its vector points. Farmer has vector points. They get merged. We get a forward vector. We know how those vector points are being adjusted. When we get a forward vector, that means farmer and reasons buy seeds are greatly independent on each other. So now we use those values that we got after the dot product to update the vector points of the farmer, which again is used to update the probability and reduce the loss. So that's how the pattern is being traced in tab transformer. Yeah. So time factor, I will just progress. So so this is how we evaluate. Now, tab transformer, we had one problem, computation resources. So, and then another thing, it's also data hungry. So I was just testing it. If algorithm is good, might be actually important, we consider trying it in the future, given we get enough data set, because it needs over 100,000. Yeah, at worst 50,000 rows for it to be able to run. Then computer it wants to run on GPUs. Yeah. Yeah. So because of computer and the data resources, we're just testing it out and finding out how it performs. Yeah, I tried. And then in computational resources, we just did only one split on it. And our condition in the code, we defined minimum number of splits as 3. So since we defined minimum number of splits as 3, tab transform or whatever is here, it did one split, is not the average. And therefore, we cannot guarantee its stability across circles, different circles, because it is only one. So the reason as why we don't want single split on a single split due to the circle robustness issue. So we don't guarantee this, we drop it out. So on comparison and evaluation, everything, overall winner XGBoost leads the stability average of F2 and everything across 6 splits. So that means my module selection goes to XGBoost. That's how we made the module selections. So MVP readiness. So yeah, our modules are ready as MVPs for deployment. Why? Because the leakage sensitive columns, we removed circle evaluation. We hardened them with random splits and the stability runs. No cross split duplicates found. We checked all those IDs. We removed sharp drivers. We removed. So we proved their stability, and yeah. So as MVP they're ready, but final production not yet. Because why? Because like things like look, so like threshold still vary. So across different circles, you saw the deviation, how the threshold was varying across different circles. So that means there is going to be always variation in how the module performs, depending on the circle, where the circle is coming from. So we are going to be working upon that. So so this is our deployment plan. So we run alongside current process. We log predictions. We do not change decisions. So we track the circle drift. So we do assisted decisions, and then we do policy integrations. So summary, key points, leakage-free design. So and then smoke gun found, circle disjoint evaluation. So thanks for listening. And finally, XGBoost is still the module I'm using. So thanks for listening. I remain Mr. Joseph from Lendshield AI Research Group, Makerere University. Thanks.